In this installment, we'll talk a little bit more about tires and how tires work and the friction. In this first image here, one can see the tread grooves, and you can see the water that is going in the grooves, and it's being sent sideways off the tire, which allows the tire to sink, not hydroplane. It allows it to reach the ground and have traction on the road. In the image below that, we can see a number of different tires for different conditions. So when we look at, say, for example, this one here, which is more like a racing tire, what we see is there's not a lot of grooves. Well, generally the racing is done on dry conditions whenever possible, and they strive for dry conditions, but they're also trying to maximize friction. With very large, powerful engines, that's a lot of force. And for the wheels not to spin, if you peel out, if you give it too much gas and the wheels spin, then there's no friction, and there's no traction, you don't go anywhere if the engine is too powerful. For the tires, so we want to increase the surface contact, so to increase the friction. And on dry roads, we don't need so much movement of material outward. When we look at this tire over here on the right, we can see that water could be squeezed out in the back direction or the forward direction, like so. And any out near the edges could be sent outward as well. And so this we could see is we want to get rid of the water side to side, but it's not like it's needs to get rid of a humongous volume, but this channel here is pretty deep. You can also see now why when the tire tread wears down, these wells that have a depth to them allow it to carry water out. But as the tread wears down, those channels become shallower and shallower, able to move less and less water, and it becomes increasingly likely that you'll hydroplane. And this tire pattern over here, more in the middle, we see these channels to move the water forward and backward, some smaller channels to go to the side, but there are these others that crisscross and sort of dead end. It's as if it traps material, and so this gives it more traction, as if it can grab. Rather than pushing water out to the side, it gives it some grab. And we see some more of that in this case. Yes, the water can be pushed out, and maybe if it's slushy snow can be pushed out and to the sides, but there are these grooves that are designed to capture and hold and grip. In extreme case, we have in this tire up here, we see these massively deep grooves that although they can push outward, they're designed to really trap material. So we can picture these being filled with sand, or we could picture these being filled with snow, pushing the snow into these channels so there can be some traction, but the snow itself does not need to be moved. So it's deep snow and mud and sand conditions. And then we have a more intermediate type tire here where we can push some of the material out forward and backward, but there's also this notion that you get a little sense that you're going to trap some of that material for traction as well. And so each of these tread patterns has a different purpose for moving different types of material, and that's why we have all-season radials. And we have snow tires. And so they're different from each other in terms of the tread pattern, their ability to move the snow and the water and the slush out versus gripping and grabbing it. So the tire treads do play a role. So I've mentioned hydroplaning a couple of times, and we spoke about the effect that water has. Let's look at this in a little more detail. Under normal conditions, what happens is the tire is able to move the water either forward or backward so it can have contact. That's these grooves here that we see, like so. They're able to move the water out, and the tire can make contact. When hydroplaning occurs, it's not able to move the water out, and so the car rides on a plane of water. And you could do a YouTube search and find some videos of this, and you'll see that when they take videos of cars that start to hydroplane, the wheels stop spinning. Although the car is still moving down the road at, say, 50 miles per hour, whatever, the wheels stop spinning because it's just actually skating on top of the water. Let's speak now a little bit about tire inflation. We have 3 cases up top: underinflation, and we can see the effects there. Overinflation, it kind of hyper balloons out, and proper inflation, like so. We can see the wear patterns. The wear is even on a tire like this. Here, the wear is in the middle. And not so easy to see is that the wear occurs on the outside of the tire. So each of these tires, then, you could measure the force that the tire exerts on the ground and its points of contact. And so what we have is 3 tires with different levels of inflation with the pressure grid showing the footprint. What I'd like you to do is pause the video and see if you can determine which goes with which tire, which picture goes with which tire. Perhaps the easiest one to connect is the one at the bottom, where we can see these 2 ridges where the greatest force is, and that would go for the underinflated tire. If we look at this the tire at the top, or the imprint on the top, what we can see is numbers that get up to as high as 2.67. And if we look at the one in the middle, the tires are 3.179. So overall, what we see higher values here, which means the force and the weight is concentrated over a smaller area. And that corresponds to the middle tire. The proper inflation, we see the weight distributed much, much more evenly, much more symmetrically, and we have lower values of pressure. And so that tire pattern goes with the proper inflation.